Yeah, yeah. So okay, so I have organized this in two parts. One is which is the major part. It would be rather pedagogical and more like a review, and I want Shiraz about it. And the second part is kind of things we have been doing with my student Aman Kumar. So the first part is the main part, which is the decay of Landau quasiparticles. Okay, so we most of us have encountered Landau Fermi liquid theory in some way or the other, and the gist is that there is a one-to-one correspondence of the low energy excitations of a system of short range interacting fermions, central force, and eigenstates of a system of non-interacting fermions. So barring phase transitions, you can have you can show there is a one-to-one correspondence of these low energy excitations. For example, you can label the excitations of the interacting system by momentum, which is a conserved quantity in the presence of two body central forces, and spin, which is also a good label. So these excitations are called Landau quasiparticles, and from this basic assumption, Landau constructed the whole edifice of what goes by Landau Fermi liquid theory, and it was motivated by the experiments which are fairly ubiquitous, and what we see in our daily lives is that even though the electron interaction in metals is not weak at all, yet the properties of most metals are explained by assuming the electrons were not interacting at all. So a characteristic feature of a Landau Fermi liquid in terms of these green functions is that if you compute the single particle green function, it has a similar pole structure as non-interacting free fermions. So it has a simple pole. This comes from the imaginary part of the self energy, and the Z is a quantity which is called quasiparticle weight. It's less than 1, and it's because of whenever you try to excite a single quasiparticle in a Fermi liquid, you excite a lot of garbage also. You excite particle hole pairs, more than one of them. And all that is, and besides that, there are some high energy processes also which are involved, and all that is encapsulated in this Z. And since you are looking at a pole very close to this omega equals to E k minus I gamma by 2, you just have this practically as a constant for all calculation. Okay. Now these quasi-particles obviously are not your exact many-body stationary states, and they have a finite lifetime, which is gamma star. And one of the early achievements of Landau Fermi liquids was a computation by Khalatnikov, who calculated using phase space arguments that the width of this pole, quasi-particle pole, goes like the square of the energy of the quasi-particle itself. So these quasi-particles, as you get closer to the Fermi momentum Pf, become rather well-defined excitations. They have a finite lifetime. So even though they have a finite lifetime, they are nevertheless a good approximation to the many body states, since the decay rates are much smaller than the corresponding energies of the quasi-particles.
Requirement of the central force. So in those models in which you have, let's say, nearest neighbors and in this direction, and next to nearest neighbor in some other direction, and so on.
So those will require a decoration of the Landau Fermi liquid. So Landau's assumption was to write an energy functional for the quasi-particle energies using these assumptions, but you can relax them systematically, and those will then begin to look different. But you can construct. Yeah.
Left-hand side is represented in interactive theory, but only for K near PF.
Yes, that's the point. Only for K near PF. Okay, and so how is the quasi-particle lifetime estimated? Well, the quasi-particle decay rate is usually obtained through using the Fermi Golden Rule simply, and imposing energy and momentum conservation restrictions on the final states. So if U is the matrix element for 4 fermion interaction, and I assume short range interactions, then the decay rate is proportional to this U square, and times a delta function conserving momentum and a delta function conserving energy. So you have P1, P2 incoming and P3, P4 outgoing particles. So these phase space restrictions on the outgoing states lead to the characteristic energy squared dependence of the decay rate. I mean, it's quite straightforward to work this out, and you will get.
Two particles in one hole.
Yes. So a single quasi-particle decays into a particle-hole pair and another particle. Two particles in one hole. And you can have further showers, which is what the talk is going to be later, that these further can decay, and so on.
So this E of P1 here, this is the free particle energy reduction.
Yeah, these are free particles. So this is a small perturbation, which is the interaction, and this is just everything in free particles. All these energies are free particles. Okay, so the validity of the Fermi Golden Rule, of course, rests on the assumption that a continuum of states is available for the decay products. And obviously, this is not a problem for an infinite system. The other thing you want is that the matrix element U connects a large number of states in the continuum. You just can't have such a small interaction U that it is only able to perturbatively correct energy levels which are rather far away from each other. Then there is no decay. There is only sort of perturbative corrections to the energies. Yes, it would enter. And in any case, this Fermi Golden Rule assumes that there is a continuum of states you can go into. Continuum is, of course, in a relative way. This U has to be big enough compared to the mean level spacing. This will come up in a moment.
But doesn't U have to be small in something, and there's a fourth order term which will also give you
yeah, U has to be small compared to mean level spacing. Yeah, that's the whole point of the talk. Yeah. Okay, so now come to a finite volume, which is what this talk is about. So in a finite size system, the energy levels, even at the level of non-interacting particles, they are discrete. And for the Golden Rule to be justified in a finite volume, this mean level spacing delta, which goes, let's say, inversely as the size of the system, volume of the system, should be much smaller than the interaction matrix element U, as well as even the energy of the initial quasi-particle. In fact, for quasi-particle energies which are comparable to delta, the effect of small interactions, as I said, is only to give you perturbative corrections and not a finite lifetime to the quasi-particles. Okay. So this suggests there should be a transition from an ergodic or chaotic high energy regime where the interaction causes transitions between a large number of closely spaced levels relative to the interaction strength, and a non-ergodic regime where the quasi-particles do not relax at all.
So when you say do not relax, even in some long time limit, you will not.
Yeah, that's the claim. Zero. Yeah. Zero relaxation. Not expectation, this will be shown in arguments, but this is, of course, if U is very small compared to mean level spacing delta, then you won't cause a mixing between a large number of levels, and you just have perturbative corrections order by order, and they will just shift the levels around. They won't cause transitions. So exactly, yeah.
But some high order it will,
No.
I understand that
No.
order by order in all orders?
Yeah.
I think he's saying the imaginary part won't arise.
Exactly. The imaginary part doesn't appear, right? So you only get real. Yeah.
This is the same reason that you have an absolute hole in an insulator.
Yes. It's the same thing. Yeah.
Suppose you got an insulator when the hole is the first thing is separated by a gap. And then there's really an absolute hole.
There's no continuum available to decay into it. So you need some matrix element connect.
Yeah.
Okay.
Yeah.
Yeah.
If it starts a continuum, then at the bottom it has nowhere to go to, but yeah.
So when I have the last electron here and nothing above it.
But if there is a conduction back, then
Then there's a continuum, of course. Continuum, of course, yeah.
For this band, yeah.
So,
And the gap, right? Again, when you have a gap,
no, I think the question is whether you're talking about a finite gap or if you just take a one band model, then there's an infinite gap. There's nothing there.
no, let's take a finite gap. Even so, this guy is like absolutely well defined in space, right? Or not?
That I'm not clear, that is the excitation from here to the next guy, which is coupled to the continuum. Which is coupled to
yeah, continuum you should not have anywhere nearby.
But it doesn't
Otherwise,
matter. So I mean, I thought it was sorry, you used to correct me, but I thought it was basically a question of whether you can use whether you have to use degenerate perturbation theory or non-degenerate perturbation. When you're using non-degenerate perturbation theory, you get small corrections to your energy level. The degenerate perturbation theory is huge. And this was my feeling. This
I'm just not 100% sure if the state is separated with a gap with a continuum. I don't, that's the only, maybe I'm.
no, I could be wrong, but I don't think it matters because it is separate, right?
Suppose.
Yeah.
okay, so if there is indeed a transition or a crossover, is there can we imagine this characteristic scale delta or something parametrically larger? Like my point is that is there some energy scale epsilon, which is say some multiples of delta in some way, which demarcates a region where the streets, the levels can be essentially treated as continuous, and below which Fermi Golden Rule doesn't hold, and you basically have infinitely long-lived states. So phase transition you can do as a function of energy. You can tune your energy. You can tune your interaction parameter. You can tune various things, but I'll just clarify in a moment. Yeah.
Here's the answer with the G sitting in it. The way you were saying it didn't matter what interaction scale I put in.
It would matter if the interaction scale got comparable to the gap between this thing and that.
Absolutely.
So I mean, I'm probably wrong, and Vikram will correct me, but what I was thinking was that suppose you've got your free particle thing has some scale, has some delta, and you've got an interaction that's small compared to that.
Okay.
Then all you will do is renormalize energy levels one by one.
That's what I'm saying. Yeah.
You think order by order some perturbation scale.
And even finally, you just shift it around a bit.
Yeah, that's
Yeah.
that's
With multi-particles.
That will persist
Yeah.
for every order because you will gain
Yeah, yeah.
factors of u in the numerator.
But there are denominators which are deltas, which are bigger.
Gain more and more factors of delta.
Hmm.
no, I mean absolute zero versus saying it's small in some higher order is
Just u by delta.
Yeah, absolute zero requires some care, and that is what you. But imaginary part won't develop, is the claim.
Yeah. See, suppose you have an electron. It mixes with two electrons and a positron. So because the electron has a mass gap, the two electrons and positron, this first state with which it can mix, separated from the electron by mass. This is enough to tell you that there will be a mere pole for you.
With some broadening, but
No, I mean, a genuine
broadening would be zero.
No, the delta function code, suppose you compute the propagator. Okay, there will be a genuine delta function, not with strength 1. The strength may be half, but a genuine delta function. It will be a real electron state.
On the real axis or on the complex?
No, real axis.
I'm not so sure.
No, because, you know.
Because that essentially means there's no broadening. Exactly no broadening.
Yeah, there really is an electron. That's the electron is state 1.
I'm saying that's a more of a statement than just saying there's a pole with a broadening.
I'm thinking genuinely, without any problem. Because there is, the first thing it can decay to is separated from it by a gap. By a big gap.
but what if there's a continuum?
It doesn't matter.
How do you think
No, it doesn't matter. I mean, it doesn't matter because, you know,
what does
The continuum is upwards.
Exactly.
That is the
That's the point.
Okay.
that's the point.
Yeah.
Fermi Golden Rule will apply, but only if you put in an external system.
Yeah. Right.
You know,
And there's a threshold to that external system. If you know that,
sorry, Vikram,
Hmm.
sorry, but delta was the inter.
Yeah, this tiny single particle level spacing in.
ET was the interaction.
No, no, ET I'm going to explain. Right now I still haven't started it, yeah. So, so
Electron interaction strength is V, right?
so
That is not ET, so I didn't understand what.
yeah, so this I'll come, this requires some explanation. So this is specific to the kind of system one is studying here. Okay, so let's begin with a very well studied system, which is, let's say, a conducting grain of size L, and let's say the electrons can move around in it diffusively because there is some scatterers there, and electron motion is diffusive. The diffusion constant is d, and it's related to the conductance of the grain. So if you put some leads on it and try to measure its resistance, or inverse of that is conductance, then call it G, then this is going to be basically given by the following quantity. There is an energy scale called Thouless energy scale, which is the energy of diffusion at the length scale L, measured in units of the mean level spacing small delta. This dimensionless quantity is the conductance of the grain, and if the diffusion constant is very large, meaning which is a well conducting grain, then this dimensionless conductance is large. Now this quantity ET plays a major role in the theory of Anderson metal insulator transitions, and its name is due to Thouless, who identified this as the scale involved in determining insulating behavior from metallic behavior. And what Thouless did was, like he said, let me consider two systems, two grains of this kind of size L each, so that the combined system is size 2L, and let us say I weakly connect them through some matrix elements whose strength is T. And so inside this grain of size L, as well as here, there is a mean level spacing which is small delta as usual. And what this T does is, due to hybridization of energy levels on this side, you can imagine that you can get some broadening proportional to this small matrix element T square over delta. And when this quantity becomes comparable to delta, then this broadening starts mixing various energy levels, and you can say that then these energy levels of these two boxes no longer remain distinct from each other, and there is a sudden reorganization of the wave functions. They will fill up the whole thing, and you need to think of wave functions that occupy a full volume 2L. So this marks, of course, the delocalized state, and if the wave functions remain well defined wherever they were, then that marks the localized phase. So this is the crossover. So there is no proof right now that this is a phase transition, which is later, but this is a crossover scale, and the crossover scale is given by T square by delta square is 1. And if you see, this Thouless energy scale is simply T square by delta. So this then is nothing but my dimensionless conductance, because this is E Thouless over delta. So when the dimensionless conductance exceeds 1, that is where you expect a metallic like scaling of this conductance. And when the dimensionless conductance is less than 1, that is where you expect states to be localized. So Thouless correctly identified the dimensionless conductance as the single parameter that controls metal to insulator transitions, and not conductivity, or just not the diffusion constant, not the conductivity, but the conductance. T is some small matrix element connecting energy levels here with some energy levels here. So you can say one to many kind of thing you can connect. And this gives you T square by delta is a measure of the, again, Fermi Golden Rule like thing. So this
You said this, Vikram, but I was taking out the D was, you said
diffusion constant.
And
Yeah.
what is that in terms of microscopic parameters roughly?
So if you have some scatterers in the conductor such that the mean free time of scattering is tau, then the diffusion constant is Fermi velocity squared tau by dimensions. So this you can forget, but it's basically Vf squared tau.
These are elastic.
Elastic scatterers, yeah.
Become one question.
Hmm.
This seems to be in a more modern language, the arguments that Thales makes would be more in terms of how entanglements scale. And anyone actually tries to make, you're talking about something which is delocalized over the whole box versus things where there are wave functions in one box and another box. And if you look at the entanglement entropy of some typical state, when making a cut, they would behave very differently, like if they're localized versus delocalized. I was just wondering if anyone has actually looked at that problem numerically with some disorder and actually tried to.
I don't know, but would make sense, right? Because it's an ergodic, non-ergodic kind of transition. Yeah.
Volume like versus area like, whether people have actually tried to make this more precise by looking at that kind of thing.
Vikram, I'm really sorry, I didn't get what you said here. Could I request you just repeat what you said on the body?
This is Thoules's hand-waving argument. Why this E Thouless is a very important scale governing a metal insulator transition.
Could you say it one more?
Okay, so before that there was this concept that, you know, conductivity is essentially given by this Drude formula, and you have this mean free time of scattering. You can rewrite this, and it turns out that this can be written in terms of mean free path also. So you can do Vf tau and then divide by Vf. Okay, so this is mean free path which cannot possibly be smaller than the lattice constant. That was the claim. So once the mean free path starts becoming comparable to the lattice constant, you should reach a minimum conductivity, sigma minimum, below which you should have an insulator. So this was the misunderstanding. It's called the Joffe-Rigel criteria. And until Thouless came up with his argument, which I'm going to again rehash, this was believed to be the condition for deciding whether you are going to be a metal or an insulator, that your mean free path of scattering should be comparable to the lattice constant, and below which you are an insulator. But he said this doesn't matter at all. What really matters is the dimensionless conductance of the system. Now, if a system is a metal, then if you take, say, a chunk, a cube of copper, and you increase every dimension by a factor of 2, then you know that it will become even, the conductance will even fall. Why? Because in 3D, your conductance goes like sigma times L to the power of d minus 2, so it increases, where sigma is presumed fixed. But identifying this as the dimensionless parameter controlling a metal insulator transition was Thouless's contribution to the field, and it goes like this. It was hand waving. So what he said was that let d be the diffusion constant, so that this is the energy of diffusion. You can actually relate it to these quantities. I'll come in a moment. So let's begin with two chunks of metal, each of dimension L, and mean level spacing delta, which is small. And let's say T is the matrix element coupling these energy levels to energy levels in this box. Okay. Now, if T is very big compared to delta, you can say that Fermi Golden Rule will be relevant. It will be valid, because you can mix large number of states due to this T. On the other hand, if T is much smaller than delta, you will only get perturbative corrections due to, again, the kind of thing I was just saying in Landau Fermi liquids, to these levels delta, and there will be no lifetime, meaning the states remain where they are. They don't leak out. Okay. Localized. So the criterion for Fermi Golden Rule's validity is T square by delta is comparable to delta.
Now, where do you get T square by delta?
T square by delta is the Fermi Golden Rule. Yeah. This is for T much bigger than delta.
One thing which I never understood.
1 over delta is the density of states here.
One thing which I never understood about this argument is seems to completely ignore the kind of states you have. Just as the mean level spacing and T. And you're making a local perturbation around the edge.
Yes, the kind of state is given inside this.
Yeah. Like
Kind
the
of state is written in
yeah. The overlap between states is dependent on how much existence they have at the boundary. So sensitivity to the boundary conditions is what determines a metal from an insulator. So clearly, like, there is something happening when this becomes, the broadening becomes comparable to the value of the energy spacing itself, and this is nothing but your Thouless energy scale, T square by delta, and that measured in units of delta is your dimensionless conductance. So G order 1 separates a metal from insulator.
Why is that same as dimensionless conductance?
Actually, you can show by microscopic modeling that this quantity, when reworked, assumes this form. There is, yeah, it should.
T gets related to your T, that means.
Yeah. So T is like, yeah, I mean,
Because you
this can be shown.
then to your
Yeah.
elementary path or something.
Yeah, absolutely. So this can be shown. I just won't have the chance to show it here, but yeah, it can be shown. And so the claim is that G equals to 1 is order 1 is what separates metal from insulator. It's true, in fact, if you take a long wire of more than 10 kilo ohms, which is what G equals to 1 means, then what will happen is as you start increasing its length and you are at really low temperatures, its resistance starts scaling exponentially with length, not linearly with length. Yeah. Very low temperatures. So if you are at finite temperatures, you always end up seeing something more dominant, which is called variable range hopping. But if you go to really low temperatures, this is how it scales. It is a second order perturbation based argument, right? Yeah. So you can see that this Fermi Golden Rule is playing a key role in all these considerations.
So Vikram,
Yeah.
in this way of thinking, the distinction between metal and insulator is whether G goes as a power law or exponential, right? Is that
Yeah,
how
yeah.
Not the temperature dependence of
No. This is all zero temperature. This is all zero temperature.
And delta, can I roughly think of as 1 by S?
Delta is 1 over V, let's say. Yeah. Is Fermi energy divided by volume on total number of electrons. So that's the rough scale. Yeah. Total number.
But V is different. Your V there in the last line.
I'll come here. This is not intuitive. So okay. So this was the argument in this paper, that G equals to 1 basically separates the two regimes. Now this is of course a claim without substantiation here, but if you have such a random grain, like grain with
Delta is the energy between from the filled Fermi surface to the next unoccupied level.
or any level, any two nearby levels. So on the average, yeah. And since the model doesn't have any special symmetries, there are no degeneracies to first order approximation, and therefore you can say that there is a uniform mean level spacing delta. So now this one, so if suppose you diagonalize the non-interacting Hamiltonian, so you don't have block states, of course, you have disorder. You diagonalize it and you get some complicated wave functions in space. But once you have diagonalized, the problem is essentially like single particle, and it will be of the form E alpha, C dagger alpha, C alpha, where these alphas label the eigenstates of the single particle excitations. So if you do that, you can write down now the electron-electron interaction in this basis of these eigenstates. And in this basis, it turns out that the Coulomb interaction need not always have this uniformly repulsive positive sign always, but it can fluctuate. and you can calculate the RMS value of this matrix element of the short range Coulomb interaction, and it can be shown that the RMS
It need not be repulsive because it's not just electrons interacting with electrons, or even among electrons.
among the original electrons it's always repulsive. Yeah. Electrons it's always repulsive, but you can have fluctuations above that, on top of that, which are due to base value.
Yeah.
So this is the RMS value of the fluctuations. Okay, so this is the RMS value of the Coulomb interaction fluctuation. It comes for those who know what I'm talking about. So if you have this vertex, electron interaction vertex, and you want to estimate what's the Coulomb interaction strength, then what we normally do in this theory of disordered systems is, so you have two incoming and two outgoing. So these double railway lines, they are called diffusons. So what happens is that you have repeated scattering of electron hole pairs by impurities. So these are impurity lines, and this combined thing behaves like an excitation. It has a propagator in momentum space which looks like a diffusion. So there are two diffusion poles here. So it's 1 over d squared, and then you can do various things. And so the main point is that if this was some vertex with strength u, so this whole thing, which is the RMS value of the fluctuation, goes like u square by d squared. And if you put appropriate dimensions, etc., and q cannot fall below 1 over L, you will get in momentum space the value of the matrix element for this RMS fluctuation is just delta over g times u square, but u square is some kind of a boring quantity which is constant, and I keep it out. But main thing is it's inversely proportional to the variance is proportional to 1 over d square. So this RMS value goes like 1 over g. So this makes sense also. If you have very highly conducting grain, then the effective Coulomb interactions between particles basically get suppressed by the conductance, high value of conductance. This is due to screening, of course.
So I guess the lucky thing about both these arguments is that you take into account the effect of scattering with doing scattering partially by doing this.
Yeah.
But since you can't go beyond that to increase fertilization, then you use that as your diffuse function to make the argument for what will happen beyond.
Yeah, thanks.
And what you left out is either the inelastic scattering or just going beyond fertilization.
Going beyond this, going beyond diffusions.
Any vertex between one line here and another line here.
All sorts of processes not covered by this.
You just do this much, you will get diffusion. But you know that you will not be the final answer. So then the rest you make an argument.
But aren't you also neglecting interactions in this thing? I mean, once I have a particle hole propagator, shouldn't I have a RPA bubble type thing?
Sure. Definitely. Let's come to that. Yeah.
So the diffusion thing does not have a mass.
Yeah. Because the particle hole excitations cost nothing. They are
This omega is square root of
is a frequency. It's that's the
sorry, where is the mass?
there's no mass.
It's about the Fermi surface.
But then where does delta enter? That is,
What
that is
delta?
not because q cannot become smaller than something, and that gives you a delta.
Oh, you mean just dq squared?
How do I read off the mass from
The
Q can be order 1 over L. And
q, the minimum value of q is 1 over L.
so there is no d over L square would be a.
D over L square is your E Thouless, which is what you would get here.
You cannot take that equal to 0.
You can take it in an infinite conductor, but this is finite. Yeah.
So the integral, any kind of integral over Q will start from some
1 over L.
1 over L. It's actually a summation with spacing 1 over L.
Yeah, summation with spacing 1 over L.
You're computing the propagator psi by psi. Is that?
Yeah, it's density kind of.
And this is like a
No,
curve.
it's not chi by chi by chi, chi by chi.
It's
The density.
it's not the green function, it's the density.
Propagator of psi by psi, right?
Propagator of psi by psi. Yeah.
Psi by psi with psi by psi.
Yeah.
And this is the kind of thing you do in hydrodynamics.
Yes.
So this is like a charge current kind of two-point function,
Yes.
and therefore controlled by decay.
Yeah.
Low.
That's it.
Yeah.
But if you take further effects into account, it need not remain diffusion. That's the downside.
It may not have, meaning hydrodynamics can break down even
You
if
can
it's
localize, right? It
Very
is-
localized.
Yeah, that you don't have in hydrodynamics, of course. This is a quantum effect. Yeah. Okay.
Because hydrodynamics you said that delta T below anything. That how you take the limit.
And is it obvious to see that the D, this capital D, which looks like a wave function in a relation of the, I mean the Z value of this pole 1 over Q square minus something, that is the same as the diffusion constant?
Yeah, because you see there are two diffusion propagators. So this is the quantity that determines the leading contribution to the fluctuations of the Coulomb energy, and it has two diffusion propagators. So it will have 1 over dq square minus I omega whole square in some way.
Yeah, that's the parameterization of that
Yeah.
propagator. And why is that capital D the same as the diffusion constant?
Because this capital D is the same as the diffusion constant. This you can show, like it's a like it's not easy to show in the blackboard, but
transform that, you will get the diffusion property.
you will, yeah, if you just take the Fourier transform, you will get the usual relaxation, exponential relaxation which you get for the diffusion.
From hydrodynamics it's there.
Yes.
But why you are getting this? Well, it requires some, yeah.
In hydrodynamics, J is equal to D times gradient of charge.
Yeah, but
And then
the
charge
other
conservation.
question, if you cannot take the hydrodynamic limit,
Right.
you are still using that hydrodynamic propagator here. Right, because by the, okay, delta is an important scale, you cannot go to that Q0 limit anyway.
So all these make
So
sense
taking that
from the
form,
top,
you
yeah,
can
of
say
course, yeah.
maybe it holds, yeah, right. Go on with that.
Okay, so now I come back to my line. Yeah. Okay, so now the quasi-particle decays into a shower of m plus 1 particles and m holes. So simplest case is of course m equals to 1. That's a particle hole pair and another particle. Okay, so now what I will do in the rest of the talk is consider highly energetic quasi-particles whose energy is way bigger than the mean level spacing delta, and then I ask as I progressively lower epsilon, do I suddenly finally reach a point where Fermi Golden Rule type of considerations are no longer valid, and I will end up for all states below this scale infinitely long-lived quasi-particle states. Okay, so the arguments roughly go like the following.
Epsilon was what? That's the energy above.
I create a single particle excitation at some energy epsilon, which is quite high above the Fermi level in units of mean level spacing delta. Okay.
And epsilon is 0 at the point.
Yeah, and I start progressively decreasing it to see where the transition is taking.
It will cascade.
Yeah. Okay, so now when you have the first shower process, like decay into a particle hole pair and another particle, you can think of it like, how many states are available to it subject to conservation of energy. You can imagine that I have a number of quanta which is equal to epsilon by delta, and I want to distribute epsilon by delta number of quanta in 3 boxes. And it's a combinatorial problem, and the number of final states in a 3 shower is roughly like epsilon by delta whole cubed if this number is big. So if I want to calculate what is the mean level spacing, or what is the typical spacing of energy levels available for the final shower, it is to be estimated in the following manner. So the density of states of the final shower is just dn by de, dn3 by de. n3 is the number of final states available, conserving energy. So the inverse of that is my level spacing for the final shower. So this goes like roughly delta cube by epsilon square. So now this brings me immediately to the condition for breakdown of the validity of the golden rule. The validity criterion was that the levels, the density of states of the final shower times the matrix element causing the transition should be equal to 1. That's where the Fermi Golden Rule argument breaks down. So the argument is that V over delta 3 should go to should be 1, and below for all smaller values of this ratio, states are infinitely long-lived. Fermi Golden Rule doesn't work.
V is the matrix element?
V is the matrix element for Coulomb interactions, this RMS fluctuations. And what you find is that there is this energy scale E star emerges. It's parametrically larger than this mean level spacing delta. It's square root of G times delta. G could be 1000, bigger in a typical metallic grain. Which is
I don't understand, this is a different problem. So we had very long back looked at this problem of a very high energy doubler, which again you can ask how it decays if it is, and all this kind of arguments hold true. But in the end, there's also a matrix element which goes down with the number of showers you have to create. So you have to fully create them.
We'll see that. So this is just hand waving. So a real treatment comes now. So this is already giving you a rough estimate of the energy scale at which this crossover takes place, if not a phase transition. And this is much larger than the mean level spacing delta. Of course, at mean level spacing delta, you knew it's bound to fail. But the claim is that it fails much before that. The states start becoming infinitely long-lived when you are still quite far away from the Fermi level.
I'm slightly worried that your V remains V. I mean, once you get to this thing, there's a higher order.
Higher order will come. The question is whether higher order processes only lead to perturbative corrections to the energy levels, or they lead to a runoff. So let's see. So
No, they don't need to give you a runoff. They just need to give you one condition at very large numbers, order, where you can connect the energy so that you can get an imaginary path, and then you will have some runoff.
yeah, we'll come to that. That's exactly what will happen. Yeah, that's exactly what we'll do. Yeah. Huh? Breaking down at small energies. So, but the small energy, so here's the thing. So you start with some epsilon, which is much bigger than delta. You start lowering it. So here at these levels, let's say the quasi-particle decays. Then you start lowering the energy until you reach some energy scale epsilon star equals to square root of G times delta, below which infinite lifetime. So this everything I am saying is for G much greater than 1. For G less than 1 or order 1, anything I say, don't trust it. Yeah. So
And this slide is supposed to be some argument to justify the previous slide. Previous slide you already argued for G much greater than G order 1 is breakdown, and this is.
but this transition is not a metal insulator transition. The dot is always highly conducting. This transition, I'll argue, is taking place in a Fock space of states. That this is the whole idea of many body localization, which I'll bring up now. So
are you then saying many body Laplace states are infinite conductivity? Because I thought one of the definitions of many body.
no. You should never. The localization need not be in real space, right? You also know that.
No, that is
The
fine,
localization could be in some initial. Yeah.
But I'm just saying that the original definition of many body Laplace states was zero conductivity at exactly zero conductivity at finite temperature.
A single quantum dot will never give you zero conductivity. In fact, this transition occurs at in some abstract space, the Fock space of states, and when the transition takes place, it has got nothing to do with an actual metal insulator transition real space, but it has got everything to do with what's the width of the resonance. When you measure, say, quantum dot conductance, you get peaks, conductance peaks whenever you get a resonant level with the Fermi energies of the leads. And the question is, what's the width of this level? If you are many body localized in the Fock space, the width of the level will be 0. It will be a delta function sharp peak. And you will see a lot of closely spaced peaks as successive energy levels separated by mean level spacing delta come into being.
This is the new phase transition, not the old.
Yeah.
G
Yeah.
independent of length.
Yeah.
Whereas
So
this
no,
one
no, G depends on length.
depends on length.
G depends on length.
Dependence is what tells you insulatability.
Yeah.
V was the Coulomb interaction, right? Above the
V is the fluctuation of the Coulomb interaction.
Coulomb
Yeah.
above the V, right? And the reason why this is breaking down is because the Coulomb interaction is very weak in a sense. I mean, delta 3 is a scale much smaller than delta.
So epsilon. So see, this delta by epsilon is smaller. Is much bigger than 1, right? Sorry, smaller than 1. Smaller than 1. Delta 3 is small. Delta 3 is small. So this condition therefore is it requires smaller values of V, but see, the Fermi Golden Rule is always for the final density of states and not for the level spacing of the. You have started from any state, but you just have to look and see if the density of states available for the final product is high enough compared to such that the matrix element V times the density of states is much bigger than 1. Otherwise, Fermi Golden Rule is not valid.
Once you are beginning in medieval physics and then trying to do Fermi Golden Rule, because normally I can make that term much smaller by saying I have to create n particles. That delta n would become much smaller, but normally so would be the matrix element. It will go exponentially small.
Yeah.
And then that ratio is not clear that it goes down.
Let's see. Yeah, this is all which Altshuler etc. addressed. Yeah. So
Can I understand how each of these quantities scale with length of the system? G
Ha.
scales like how?
G will scale for a 3-dimensional dot like L. Like so.
L.
Yeah. So G goes like sigma L d minus 2.
Okay, so L to the d minus 2, and so square root G scales like in for a three spatial dimension space, like
Square root of L.
And delta scales like how?
Delta scales like 1 over volume. 1 over volume. So you see, none of these things I am saying make sense in the continuum. So you have to.
So as L goes to infinity, epsilon star goes to D.
Yeah.
Okay, good.
So it's only this artificial problem is coming up in the context of a finite size system.
Sorry,
Huh.
so you did this for a 3 shower,
Yeah.
and if you did this for an n showers, how come that n wouldn't stick around in your final condition?
Will. So this is exactly what Rajdeep is asking from the beginning. From t equals to 0, is asking that question.
What is the question, this one?
Question is, what about higher order processes which can negate this kind of a logic? Yeah. So okay. By the way, this has come under criticism, and the reason I'm giving this talk is it's not an open and shut problem. Okay. So it is just to.
Intuition is from some earlier problem I have solved, where at a very high order you connect and then start getting a finite answer.
Sorry, Vikram, one more question. This estimate you got for this interaction matrix element, if I just took free electrons and estimated the Coulomb interaction matrix element with those 3 states, that would
No.
be this, or would be totally different?
No, it will be totally different, right? So,
Because
for
it
example,
involves diffusion of the and so on.
yeah, it
Yeah, so-
involves dressing by diffusions. Yeah.
So you have to do something more sophisticated. I didn't understand that more sophisticated thing.
Yeah, so that I can discuss later, or whether in a seminar or whether just privately. It's not that difficult, but it's long. Yeah. So okay. So now this is what Rajdeep was saying. I'm trying to hint that there is an Anderson localization transition here, but how can I talk about an Anderson localization transition when the conductance routinely remains large and it doesn't have an insulating phase? Well, in this work, these guys argued there is such a transition in this problem, but it's in a very abstract space, and often you have a situation where an Anderson transition in the Fock space of states appears concomitantly with Anderson localization in real space. So this won't be one of those examples. So there, in that case, you get a perfect insulator. But here you will always remain good conductors, but you want to ask what's the level broadening of a quasi-particle. Is it finite width or 0 width? Okay, so here's the Hamiltonian. This is the non-interacting part which is diagonalized after taking disorder into account. And for simplicity, like you write these matrix elements of the Coulomb interaction V alpha beta gamma delta, where you have the usual 4 fermion interaction. For simplicity, this is assumed to be constant, and whose value is given by the RMS value. So what you have in Fock space is something like what you see all the time in non-interacting problems. That is, you have a set of isolated sites which are localized in Fock space. There is nothing connecting one state to another. There is no transition possible. You diagonalize the problem. But now you add another term which enables, it's a 2-particle hopping in Fock space, if you like. So you have some many-body state. You annihilate 2 particles at occupying states beta and alpha and create 2 more in gamma and delta. So it connects states having similar quasi-particle content. So it's a local Hamiltonian in Fock space.
Alphas are momentum.
Alphas are, no, they are eigenstate labels of the single particle problem. Momentum is no longer a good quantum number because it was disordered because of the impurities. Yeah. So it's a local Hamiltonian in Fock space. These V's are random with 0 mean and whose RMS value is given by what I wrote, delta Vergy. So there is this notion of Hamming distance in Fock space. Like suppose you write your Fock space as a binary number, 1 if a particle is present at a site and 0 if it's not. Then
Sorry, but by site you actually mean eigenstates of the single particle.
yeah. So site means site in Fock space. Site in Fock space.
But is there a notion of locality?
No,
Hamming distance is so I'll explain now. So you have a binary number.
oh, okay.
Okay. So you have, let us say, some. So suppose you have n number of quasi-particles to fill, and you have this kind of a state, and then yeah, in the single particle basis, in the alpha basis, then the idea is that this thing will basically annihilate, basically flip 2 of the 1s to 0, let's say, and 2 of the 0s to 1. It's the most complicated thing it can do. Of it will flip 2 1s to 0 and back again. So that's also possible. Various things are possible. But you see, all these states, if you imagine how many bits you are flipping, it's 2. And there is a notion of a Hamming distance which says the distance between, so there's no norm you can easily define, but the distance between 2 states is basically how many bits you need to flip to go from one state to the other. And that way the distance never exceeds 2. So it's a local Hamiltonian in that sense.
Few body interactions.
Yeah, local means few body interactions. What? What?
I mean, states connected by a single V never differ more than by V.
Yeah,
But I can construct states which differ by
that is true. But in the Hamiltonian, this is all that.
Thinking, I remember there was some way in which they thought of this space and just added in some detail aspects of things.
Yeah, it will come.
What is the logic to it?
It will come, yeah. So,
But sorry, just to define the notion of delocalized or localized, you don't need that notion of distance, right? You just take a state and you ask how big is its support in this basis. There is a preferred basis.
that's exactly.
You can call conceptually the single site basis.
Yeah.
And just how big is the support.
Yeah,
If it's
yeah.
spread
How
out
many
in
states
numbers.
participate?
Yeah.
That's it.
Yeah, in fact, that is the right way to think about the quasi-particle lifetime. After all, the many-body eigenstates are infinitely long-lived, and so if you had prepared it in any one of them, it would live forever. The quasi-particle is approximation. So in principle, you can write a quasi-particle as a linear superposition of the exact many-body states. So you can say, okay, and and then the question is that if the quasi-particle is a good, very well-defined excitation, it will overlap with only a, it will give you big overlaps with only a small number of many body states. And why this is connected to the notion of decay? Well, the decay comes the moment you look at time dependence. So if you look at time dependence, then you have so if there is a big spread of energies in this superposition, then oh sorry. If there is a big spread of energies, then you can see that even if you start in this state where everything is like coherently adding up, pretty soon the components will go out of sync with each other. And in a time which is given by 1 over delta E, where delta E is the spread of the energies, you will basically lose the quasi-particle. It will never come back in principle because the number of states can be very large in this spread. And so you will say the quasi-particle has decayed. It's exactly what Sandeep is saying.
Well, as long as there is a part of the state that a finite part of the state that has overlapped with only a few, that's enough.
Yeah, yeah,
Half of the states will have overlap with everything.
yeah.
Should they occur in your shape very close together, or
No, because this Hamming distance is any 2 bits. Any 2 bits. So it doesn't have to be close in real space.
This is not closer anyway.
No, it's
So there is no sense in which one alpha is closer to
yeah,
another alpha.
yeah. In fact, this again brings me to another point which yeah.
Only when you could actually try and say something close to something else. Just in energy by ordering, like look at the difference in epsilon.
Okay, so so now so this is a problem in Fock space. There are 2 to the power of n possible states possible in an n-site system, because every site could be occupied or not occupied. Okay, you have a problem of distribution, yes, but let's say this is the total number of states possible in the n-site system, and interaction basically leads to hopping between these states localized in Fock space and promotes delocalization in Fock space. So what do I mean by delocalization? A state is delocalized in Fock space if its support, which is there are various accurate definitions, but roughly right now, if the support scales exponentially with n, then the state is delocalized, because the number of states is also growing exponentially with n. So if the supports also scales exponentially with n, the state is said to be delocalized. And in this case, the quasi-particle state overlaps with a macroscopic fraction of the total number, and it is said to have a finite lifetime.
Now, suppose you've got a matrix element, but that's very small. Will you count that? What do you mean by support?
Support, I can formalize this. So it is, there is this quantity called the inverse participation ratio, which one can formally define as a measure of the support. So I'll show also some calculations later. So what is this quantity? This IPR basically measures the presence of different components of the quasi-particle in the basis of exact many body states. Now, of course, this is 1. Okay. So now this quantity, the inverse of that is a measure of support, and I can give you a very simple example. Suppose you are forget this problem. Suppose you have a problem of a free particle on a lattice. Now you can have 2 situations. One where it's when it's a kind of a traveling kind of wave, and the other when it is an Anderson localized state. So if it is a plane wave kind of solution and delocalized, then the wave function will be like, so if you calculate psi 4 dx, it will go like 1 over L. Okay, and therefore the 1 over inverse participation ratio will go like L. So L is basically, so in a delocalized state, the wave function lives everywhere in the system, and it's captured by this quantity IPR. You can calculate moments also to get more information on the statistics. But
exact many body states, I is the exact many body states. But then is it obvious that those states are localized in
No, 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 no. No.
Nothing to do.
This definition of localization has
Nothing
nothing
to
to
do.
do with no distance involved.
No distance involved. Yeah. So that is the usual one, and that is what Rajdeep asked at the beginning. So
Question of whether single particle has huge overlap with multi-particles or not.
And your notion of single particle is the single particle ambiguous. Eigenstates.
So
that was the second question I was going to. Did measure kind of invariant under this choice of basis for?
of course, yeah.
Isn't a trace rho square? Suppose I make psi bar psi, a density matrix out of psi, and then I make trace rho square. Then that makes
Yeah.
I mean, now it's, I think your definition is also correct. It's hard to-
This is a commonly used estimate of the support, but you say inverse of trace rho square?
Trace rho square. It doesn't
Okay.
have to do
IPR is trace rho.
Yeah.
Yeah, this is trace rho square, of course. Yeah.
Yeah.
IPR is trace.
Yeah.
So then that's totally basis it.
Yeah. No, 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 no. Sorry. Is it trace rho square? So,
I mean, rho.
no, it is not, right? No, it is not trace rho square. It is basically the basically how many body states are contributing to creating this quasi-particle states. If only a few many body states are contributing, then its support is small and finite. No, no, no. No, no.
Could you just write down the one?
No, for any pure state,
Trace rho square is one.
trace rho square and all powers will be one.
Yeah, these are all pure states. So, yeah.
Eigenvalues of so is those off diagonal or something? I don't know what it is. I'm sorry.
It's something else.
Instrumentally basis dependent.
It has to depend on basis.
You have one basis where you know there is support on only one.
Yeah, yeah. Like for example, let's go to this localized state here. So we are saying states are localized. In real space, they are extended everywhere in the quantum dot, but they are basically localized in the sense that once you select a single particle eigenstate, in the absence of interactions, it stays there forever. There is no process connecting it to anything else. So for an infinite system, it could be momentum label, for example. So or in a Bethe-Ansatz integrable system, just k. Okay, so.
Just to say, trace root square is wrong because when you do this, you get I equal I. So between this and this, I will.
Okay.
But then the question is the point where it scales exponentially or not invariant with respect to that's also not invariant.
Yeah. Okay, so conversely, I would say a state is localized if its support does not grow as I increase n and n becomes large. That means a localized state in any sense that should not care about the boundary. So that's the formal definition. And so as I grow n, the support should remain invariant. It should not change. So quasi-particles, which are essentially single particle like with a small admixture of many particle states, will have an infinite lifetime. This is what I mean by only perturbative corrections by the interactions. Okay. Now, how is this connected to the problem of Anderson localization, which I have anyway been saying it so obviously that it's clear, but so I thought that because many people here probably would not know what is this Anderson localization, I'll spend a very small number of slides on this, and so because a lot of you will know, of course. So this goes back to 1958. Anderson studied a problem of a single particle hopping on a d-dimensional lattice, locally hopping, and it's subjected to a random and short-range potential. So it was a very simple problem, and Anderson asked it completely out of the blue, because the story is he was attending a conference in Bell Labs, which was a conference on nuclear spin diffusion in crystals, and people were talking about all sorts of issues, why the spin diffuses much slower than it should by calculating it from some considerations. Yeah.
Suppose I had a free quantum field theory, massless free quantum field theory. Then I would turn on a small interaction to make it a conformality theory. So then, in the basis of single particle eigenstates, at any coupling, no matter how small, your thing will become delocalized in your population. Right? This would be the statement that conformality theories have no
Yeah.
force.
Yeah. But this is fine because here if you take L to infinity, that's what will happen. Yeah.
Just to get.
Yeah, yeah.
What was the story?
Story is that Anderson said, forget nuclear spin diffusion because I don't even understand how a single particle without spin would behave in a random potential, whether it would diffuse or not. Classically, all that disorder does is to reduce the diffusive constant, but it doesn't ever manage to send it to 0. So he studied it and he found curiously the diffusion constant actually goes to 0 in low dimensions. And in 3 dimensions there is a phase transition. So I think the paper did not get any citation for 2 years, and then it started. It's okay. Yeah. It's okay. So for d equals to 1 or 2, what Anderson showed is that every eigenstate of this model is localized, i.e. it decreases exponentially at large distances from some point, and it has finite support in real space. Meaning if I write the state as a linear superposition of position kets, then the IPR which I define in this manner, like I did here, is finite. Now for d equals to 3, what Anderson could see, but he didn't really analyze it in detail, is that if you consider states below a certain energy scale, then and this energy scale is called the mobility edge, by the way, then all these states are localized, meaning they will decay exponentially with distance at large distances. While those states which are above this mobility edge energy scale are extended. And the concept of mobility edge, of course, was greatly developed by Neville Mott in the 60s. So now an Anderson metal insulator transition is.
The energy scale will be roughly the height of the potential.
So no, in fact, in fact, the transition roughly occurs when the width of the disorder distribution becomes comparable to the hopping energy. So it's what you're saying. Yeah. Yeah, so that's the thing. It's not easy, and the paper is long, but Anderson worked it out to show that there is absolutely no delocalized state in d equals to 1 or 2. I try to imagine it in hand waving ways. I don't know. It could be that you look at it from any height. It is because it's homogeneously disordered. You can always
What are the assumptions about the model?
just some random short range disorder potential and uniform hopping between neighboring sites.
So this is the calculation I once tried. Suppose you got in 0 plus 1 time. That is very simple. Suppose you just got your impurity is a matrix. You have a transition element and a reflection. And then you keep these transition and reflection elements fixed, but you would randomly spread out the distances. Now you got some transition and reflection, so then it propagates a random distance to the next one. Now you just sum these phases and look at infinity. Because of the incoherent adding up, you get 0.
So it
One dimension is very obvious to me. One dimension for the wave mechanics. Hard to imagine not get 0. It has got something very regular for you to not get 0.
incidentally this kind of property also
Just quantum mechanics with these random, the reflection matrix. Yeah, because in one dimension, all that a localized thing does is captured by a 2x2 matrix. It's very easy to do.
In fact, in 1D, I think the fact that you can either forward scatter or back scatter. These are the only two options. Constraints your possibility.
and
It's more difficult and it's more subtle. It's some log effect. Right?
yeah, it's a log effect in 2D. So now incidentally this physics is also commonly seen in real life. So if you take a transparency which most of you have never seen in your life, but if you take a transparency, it's like quite transparent looking, but if you take 10 of them, it looks like you can see your face in it. And this is essentially the same thing, that there is destructive interference of transmission because of exactly the effect Shiraz is talking about, and so nothing gets through. So So it's actually a phenomenon of Anderson localization there also.
Sorry, Vikram. The exact location of the mobility edge perhaps depends on the nature of the random distribution.
Yes.
But the fact that it exists is
Yes.
universal.
Yes.
And that it exists at about the height of the potential is something WKB intuition would be.
But it's not always true.
What is it meaning?
The mobility edge is not always, if you do a calculation, not always at the typical height of the potential.
So in Anderson's model, it was roughly around there, but in every model, it need not be like that.
Okay. But the another thing, 3 dimensions is very intuitive.
Yeah.
Because high enough energy goes through, low enough energy comes in.
Yeah, but you could say that why didn't it work in 2D? So
Particle nature is more apparent than high dimension.
yes, yes, yes,
Roughly.
yes, that's true. Yes, that's true. And so in the Cayley tree structure I'll come to in a moment, it's even more likely that this transition exists. Okay, so Anderson metal insulator transition occurs when the Fermi level crosses the mobility edge. And what happens? The linear response DC conductance vanishes if the Fermi level is below the mobility edge, so that it's among the localized states, and unlike a band insulator, this is a very different kind of insulator. Here the insulation is not because no states are available. States are continuously present, all of them are localized, and there is nothing connecting them. So there is no, if there is no mobility edge, in fact the conductance would be 0 even at finite temperatures. You would just distribute your particles in different localized states. There is no process connecting you from one localized state to another, and in fact this is a perfect insulator.
But only for DC.
Only for DC. AC abhi aayega. So Rajdeep is like anticipating every slide.
Could I ask you, the monopole operators, when they proliferate, usually cause randomness in 2-point functions and cause confinement, which sounds pretty similar to this.
I really want to think of this problem in that manner only, as you will see as I progress, and I want to talk also. I just don't know if there is any formulation of this problem which is in this language, which seems to be exactly the natural thing to do. And as I will show that in certain cases, the critical behavior you get in the Anderson transition is identical to a BKT transition, which is brought about by the proliferation of these kinks and anti-kinks in 1 + 1D, let's say. And in that case, you would like to see if there is some proliferation of vortex-like excitations here also, which causes appearance of very strong, because these vortices are associated with very strong phase fluctuations. So the number gets progressively well defined, and you get an insulating state. This transition should somehow be connected to that kind of a confinement deconfinement thing, and this is what I am dying to understand, but I don't know. In fact, I don't have the language.
I was going to ask, in Poinakov, when trying to demonstrate the 3D QED for instance, 2 plus 1, yeah, confined, he had very similar equation. Right, that this propagator will go and then this guy will sort of randomize it a bit and then little more. But it worked up to 3 for him. Anyway, I'll ask you.
Yeah, I want to understand this, so that's the bottom line. Okay, so now that was what I said about the DC conductance, but unlike the 0 value of DC conductance, the AC conductance is finite and complex. So you can again use Golden Rule to estimate AC conductivity, and the real part of AC conductance has a characteristic singular form. This I don't have time to describe why. It's not that difficult, but yeah, it has a characteristic singular form, but not so for the imaginary part. So this is a very characteristic feature of this Anderson insulator. Yes, 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 that's the thing. Yes, yes, it's all linear response, yeah, AC conductance. Okay, so now a very important development took place towards the end of the 70s when a paper by these 4 people called the Gang of 4 appeared, because not long before there was this Gang of 4 that appeared in China, and so this was probably as revolutionary. So what they did was they used Thoules's intuition that the Anderson transition is characterized by a single parameter, and then the question is whether it's a continuous transition or a discontinuous one. So by that time it was already known that there is another kind of transition called the Mott transition, which is brought about by interactions, and Mott had argued that this is a first order phase transition, the insulator to metal transition. So what's the case here is the question. And so what these guys did was to do perturbative RG in a small parameter 1 over G. And they did it by summing some classes of diagrams which are called maximally crossed diagrams. I don't have time to get into it. But what they found is the following. I think this S is in the wrong place. So they calculated this so-called beta function, which is how the logarithm of the conductance scales with logarithm of L, and what they what they found is that it is equal to d by 2 plus some order 1 quantity minus not d by 2, it's d minus 2. I should put d minus 2 here. Okay, so let me rewrite it for. So there's a misprint. So d log g. So this is a beta g. D log L equals to d minus 2.
I think S will be d minus 2.
Yeah. So minus 1 by g. So you can forget this, minus 1 by. Yeah, this S I think need somewhere else. I think some rearrangement happened during the slide making. Okay, so you can see that the scaling, the beta function is always negative for 1 and 2 dimensions. In 1D it's very obvious because it's coming at this level itself without having any dependence on g on the right hand side. It's minus 1. In 2D this is 0, but then the next 1 over g correction is 1 over g with a minus sign, and so the beta function is again negative. So as you scale the system size, the resistance in both these cases just goes to ultimately it goes to infinite values. So now in d equals to 3, the beta function vanishes at some non-zero value of g, which is order 1 here from this analysis, and of course which cannot be accessed in this 1 over g based perturbation theory. So no one knows how to do it, of course, even now analytically. However, by the way, this is a coupling constant in some non-linear sigma model, and you calculate it. Okay, okay. So yeah, I think yeah. So my guillotine is 130 for picking my daughter. Yeah. Okay. So nevertheless, you can come up with some scaling theory. Since g is the only parameter in the problem, what I do is near the critical point g equals to gc, I linearize the beta function, and then I solve these equations. So S is some inverse slope of this beta function near the transition. So if I solve these scaling equations, I get the G and L dependence of the conductance in the conducting phase, and the dependence of the localization length in the insulating phase. And what I get is that basically I get the same critical behavior. Whatever the conductance does on the conducting side, the the localization length inverse does the same thing on the insulating side, and these you can solve directly. What is the value of S? You cannot work out using this field theory analytically, but for very large dimensions, large but finite dimensions, what has been shown analytically is that this S is half. So this someone interested how to get this can see this paper by Merlin and Fyodorov in 1994. Yeah. The model I can write down. So the partition function for the is runs over some matrices Q and S of Q is a trace of d times trace of grad q whole square plus I phi mu trace of. Okay, now these matrices Q are the following object. They, since you see to describe conductivity, since G or diffusion constant is the coupling constant, you have to have a field theory for conductivity. And so you have to carry, since the conductivity is given by a product of retarded and advanced Green functions, you need to have a field theory that carries both sectors as a railway line. So these Q matrices are basically the low energy particle hole excitations in the problem, and you integrate out all the fast electron degrees of freedom. And this is nothing but the diffusion pole which Gautam you asked about. So you can see if you take the, if you linearize it around some saddle point and you look at this structure, it has exactly the structure of dq square minus I omega, where epsilon is the energy matrix. It's diagonal in all energy indices E1, E2, E3, etc.
Is this some kind of Hubbard-Stratonovich thing done on
First you do Hubbard-Stratonovich. So first you do disorder averaging. That makes the quadratic Hamiltonian into a quartic one. Then you do Hubbard-Stratonovich in the right channel, and the Hubbard-Stratonovich field Q is the thing that. Yes. So I didn't want to go into it, but these Q matrices have are given by unitary rotations, rotations of some matrix lambda, which is like the sigma 3 matrix in the retarded advanced space. So this is in the retarded space, this is the advanced space, and these are unitary rotations. And besides that, besides the retarded advance index, there are indices related to energy and also momentum. So these are big objects, and ultimately everything is done by introducing multiple replica copies of the system, because you have to do disorder averaging, and that's the way to do it. So at the end of all calculations, you have to analytically continue everything to 0 replica number and get all the answers. So that's how it's done, and this is the structure of the nonlinear sigma model. This is like a Wess-Zumino-Witten model term. If you write in real time, it would look like a linear derivative in time term. So I pi mu trace of u inverse lambda dt u is exactly how it will look like.
Just in simple-minded terms, is this difference between the phase condition, etc., related to the property of random walks, because in 2 and less, the random walk always returns, and in higher it doesn't return, etc. So there's a qualitative difference between random walks in 2 and smaller dimensions. Can you relate that to how, because ultimately in the final path integral way of thinking, it should be just some property of
In a way, yes.
paths with randomness.
In a way, yes. So I'll do this quickly.
If it's an aside, you can tell
It's
me.
an aside, but it can be done quickly. It is correct. So, yeah.
In 2D, I thought the fact that you get threshold to 0 is a quantum mechanical level. That is not yet from
See, I can build on this, and it's sort of correct at a certain level. So you see, the quantum mechanics comes, let's say, in the fact that the electron. So you think semi-classically, but you allow quantum mechanics to creep in by saying that the electron is actually a tube. When it moves, it's a tube with a cross section which is equal to lambda Fermi whole squared. And so this electron tube is moving, and then it scatters repeatedly from impurities. And so you ask, after some time, long enough time, what's the chance that it will self-intersect, which is exactly the kind of question Sandeep is asking. And so let's say the change in conductivity, therefore, will be determined by the probability that you will intersect yourself. So how will you intersect yourself? You're diffusing. So you will cover an area dt in time t. Okay. Now how much of area you cover in time t, you cover an area Vf dt times lambda Fermi square. Okay, so you start with some short time cutoff to some long time value t, and you find that these corrections are because they are all about returning to where you started from. These corrections give negative these corrections are negative, and if you calculate in 2D, you get a log. But if you calculate in 3D, instead of the area, this will be 3/2. It will be irrelevant at long times. And in 1D also it blows up. So in 1 and 2D, it's related to probability of return. So yeah, that logic.
But something elementary one. Here, by your formula, you told us that low dimensions G goes to 0, right? At large length.
This is the initial value of G at short length scales, and GC is some critical value of G at which the metal insulator transition takes place. When GI approaches GC, the conductance goes to 0. Yeah.
No, but in low dimensions, just as L went to infinity, you told us the conductance went to 0, right?
This is 3D.
I understand.
Yeah.
So now here again, when L goes to infinity, the conductance is going 0 or no?
This is all on the this is all on the conducting side. This G is on the conducting side. On the insulating side, G is 0. On the conducting side, it grows as L, but with a smaller and smaller free factor. And this goes to 0 at the transition, and after that, only exponentially small terms are present, which are present here.
So, Sridhar, the conductance he was telling about earlier was the fate of the sphere.
Yeah.
Ei is the initial value.
Right.
That's all. And you are always coming from the metallic side. So, you will diverge if you take L.
Because this perturbation theory was
So the fate here is GC.
the
So, at GC it's critical, yes.
And if you add BI, you're attracted to GC?
So, no, it's a, no,
It's a
for 10 GC you will grow like greater than
Yeah.
each way. No?
yeah.
The transition.
Oh, so it's repulsive. Repulsive away from
It is
GC.
critical.
I see.
It's not a field.
I see.
GC doesn't characterize the field.
Yeah.
It's not a decay like kind of.
No, but come. Yeah, I'm dying to say that. So this is not a BKT-like criticality, but all my life I've imagined that because of such structures, this has to be some kind of a confinement, deconfinement transition. But BKT comes in a way, I'll tell you, in a different context. So now our problem of Landau quasi-particle decay was defined as a problem of delocalization in Fock space. But what's the structure of so you have a bunch of points in Fock space which are the single quasi-particle, non-interacting quasi-particle states, and you have some connection provided by the local connection provided by the Hamiltonian. Now, whenever the Hamiltonian comes into play, there is a number of choices available for the final products to go into. That was the density of final shower states. So this actually is reminiscent of a Cayley tree structure. So it's a forever branching lattice with no loops. Of course, in real life there are loops in the system because some quasi-particle that has been emitted as a shower can get reabsorbed, and you really have loops in the actual system. But what one can argue is that the contribution of those loops is relatively small, and the main physics is determined by this forward direction where you have a forever branching kind of structure in Fock space. Yeah.
How is it different from the Bethe lattice?
It is a Bethe lattice. So it's the same name, it's a different name, same thing. Yeah. Huh.
Forward scattering and continually creating showers would make sense in sort of some insulating links where only forward scattering you kind of care about.
So what has been done, which I won't get time to do in this talk, is that Altshuler etc. argued that although back processes are always there, their contribution is way smaller, and so to a leading order they ignored it. So there are a lot of ifs and buts about this approximation they made, and so one is. So they just counted how many possibilities are available for going back. It's a phase space argument, yeah. So it's smaller. So I can tell it to you in private, yeah. Okay, so yes, it's just got to do with that, yeah. So yeah. So what's the model? So I'm not talking yet of the interacting problem yet, but since I'm alluding that it has a Cayley tree structure, let's go back and see if people have studied the problem of a single particle moving in a disordered Cayley tree. Disorder is in the form of random potentials at these lattice sites, and otherwise the hopping element is constant everywhere. So it's a constant nearest neighbor hopping of amplitude t and random on-site potentials, which are chosen from some uniform distribution in a window, say minus w to w. So what these guys showed in this paper is that there is an Anderson localization delocalization transition that takes place. Incidentally, the Bethe lattice has effective dimensionality of infinity, and so since it's above d equals to 3, there is no reason why an Anderson transition wouldn't take place. The good thing about the Bethe lattice is that you can solve it analytically and hope to get exact values for the transition point as well as later on critical behavior of which is very hard to do in using the nonlinear sigma model approach because it gives you a small parameter 1 by g, which is not useful when g is order 1. So Anderson etc. showed that this has a Anderson localization transition at a certain value w by t equals to k log k, and k is called the branching ratio of this Cayley tree. So for this is the branching ratio is number of children. So here the number of children is 2 from any point, and so k is if it's much larger than 1, then this is the value. For the general k you can show it to be a very complicated thing, but this is the way it goes for large k, and this is the case that will be relevant for us. Okay, so how does this weird thing come up? And this also brings me to Shiraz's point in the past that if the transition always takes place when w by t is order 1. So not always, as you see here, k log k can be much larger than 1. Why? Because the volume increases exponentially with distance, whereas for all finite dimensions the volume increases power law like. Okay, so now what do we know about the critical behavior of this model? Well, this has been done in this beautiful paper 94. So what these people showed is that on this Cayley tree, as you approach the transition from the metallic side, the conductivity goes to 0 as a BKT law. Okay, and this okay, and likewise if you calculate the inverse participation ratio, what they find is something very weird. They see a jump at the transition point, with inverse participation ratio is 0 on the delocalized side and it is finite on the localized side. So it's very much like reminiscent of the jump of the phase stiffness in the BKT transition. So these are my wild thoughts, but I think it looks very BKT like. And in contrast, if you do the same thing for a d-dimensional lattice where d is large, then one can show that the conductivity vanishes as a power law, and also the inverse participation ratio vanishes continuously as a power law. So this jump as well as this BKT like law is only for the Bethe lattice. So BKT scaling suggests that of course a single parameter scaling theory may not be correct. There might be some other parameter involved which might be similar to the vortex fugacity you have in BKT. I don't know. This is just a wild guess. So current debate is of course focused on whether there is a further crossover transition in the delocalized regime between an ergodic delocalized state and a non-ergodic delocalized state. These are all technicalities. Yeah. I actually don't know, so this is just wild speculation. In BKT, like why it is BKT, I also don't know that. It's coming as a result of some exact calculations on the Bethe lattice. It's why is it exactly BKT is not known to me at least. Yeah. So, but. Oh, you get nonlinear coupled scaling equations for both the interaction parameter and the fugacity. Like you might be familiar with the coupling with the RG equations for the sine Gordon model in 1 plus 1D. So there you have two parameters. One is the interaction constant that appears outside the cosine, but one is the beta thing that appears with the angle inside. So the renormalization of that beta is equivalent to the vortex fugacity thing in the 2dxy model, and the renormalization of G is the other. They are so these are both coupled to each other, and the RG equation for G is not only a function of G, but it's a function of G and Z fugacity, and likewise the RG equation for Z depends on G. So it's not single parameter scaling. And by solving those nonlinear equations, you get this characteristic BKT scaling, which is different from the usual power law behavior you expect. So here nu equals to infinity.
But in here you don't have any two-dimensionality.
No, this is Kelly tree. So I don't know. It's some very weird thing. Yeah.
For the d-dimensional case, dimensional lattice of in your previous when you estimated the beta function, you got the correlation length on one side to die exponential, to die as a power, right? G minus G some.
Yeah, correlation length diverges. Diverges on the insulating side, and it's infinity on the metallic side. Yeah.
So it's expected to be a second order.
Yeah, this is second order in finite dimensions. But on the Cayley tree, it looks something strange.
So
Yeah.
that could just be some special feature of the very low connectivity on the Cayley tree.
It's very likely. It's very likely.
So if one's focus just for a moment is the continuum, then it seems more to me like a second order, a standard second order phase transition, which you're taking.
Oh, you mean to see that? You mean to say that this is also going as some power of the volume? Like G is going as some power of the volume. Say correlation length raised to some power, like psi to the power of D, let us say. And this also, since this is how the correlation length behaves in the BKT system, this is also some power of the volume, but it's exponential. The volume in the Cayley tree is exponentially growing with distance.
That's a more informed comment than I was I was just saying something dumb that at least that beta function thing suggests a second order phase transition with correlation length diverging, everything scaling with. So, I mean, which could be due to topological effects, sorry, but right, not like a BKT sort of, which is not a second order.
Yeah. Yeah, so even this you believe can be regarded as a second order transition along those same lines despite giving these telltale signatures. Is that what you are saying?
Well, I was trying to make a difference between a standard second order phase transition and BKT.
Yeah, it's possible. Actually, I don't know. So therefore I prefaced by saying it's a speculation. And so now finally I end with these things. So I have this localization transition supposedly in Fock space of states.
But the beta function calculation was not reliable for the three-dimensional, right?
You can do it for arbitrary dimensions, but it's when it was done for the Cayley tree, it was found that the conductivity goes like this.
No, I'm saying the calculation of the previous page was in the page.
There's no numerics, nothing that people have been doing?
Numerics have been done.
What does that show? A second order phase transition?
Yeah.
Like that?
Yeah.
Okay,
For 3D people have done it. Yeah. But for the Bethe lattice, you can analytically get the results. Yeah. Okay, so here there is a Cayley tree structure here also, because every quasi-particle has many children. Sorry, it has 3 children, but many states spanned by these 3 children, and the branching ratio in any generation can be showed to be g cubed by n. So the branching ratio progressively falls as you go to higher and higher generations, simply because there is less and less phase space available conserving energy. But what Altshuler etc. did was, for the moment they ignored this systematic decrease of the branching ratio by 1 over n factors, and said that, let's say I assume a constant branching ratio, and then let me work out what is the transition, what is the characteristic scale for the transition that I will get in this Fock space of states. So if you use the same criterion as this, W by T is k log k, then if you plug that in with k equals to g cubed, then you get a characteristic energy scale which is delta times square root of g but over log g. So it is almost the same as what you got for on the basis of Fermi Golden Rule arguments, but this more accurate kind of treatment corrected it a bit, but essentially you are not very far off the mark. So indeed there is a phase transition that takes place. In terms of the picture in the Fock space, the fact that an Anderson transition takes place tells you immediately that the support on the delocalized side is infinity, and therefore the wave functions will, the quasi-particles will all decay in a finite time. And on the other hand, in the Anderson localized side, the quasi-particles will be infinitely long-lived, and the critical behavior of this transition of course is known. So if you want to find the width of the quasi-particle excitations, that will go to 0 as you approach the transition from the metallic side, from the delocalized side, in accordance with the BKT law.
Here this k is discrete, but at different points you have different k's. Is it, and you have some distribution of k?
No, it's like it's constant, but we did even something more drastic. You ignored this 1 over n, which is like, is it dangerous or not? Okay. Yeah. Probably. Yeah.
Volume grows like what? Does it still grow exponentially?
Volume grows exponentially. Yeah. Because it's power law only. So, okay. So now very quickly, what you can do with this kind of a philosophy, you don't always need to be disordered. The idea is very general. So so you can ask, suppose you have an integrable system where there are some elementary excitations or quasi-particles that you know very well. Then as you turn on a perturbation which breaks integrability or anything like that, what can you say about the stability of these quasi-particle states? In particular, in the Kitaev model, it's a very interesting model introduced about a decade ago by Kitaev. It's an Ising model basically, but with interactions having very different behavior along different directions. So if you take spin half particles, then put them on a hexagonal lattice and call these bonds at every site like x, y, and the vertical bond you call z, then you have Ising-like interactions involving only some components of the spin. Along the y bonds only y components, x bonds only x components. So this is Ising-like model, it's integrable in fact. So Kitaev showed that the model is integrable and the quasi-particles are not what you expect for most spin half magnets. They are not spin 1 bosons or magnons, but they are dispersing Majorana fermions and localized Z2 fluxes. So quickly, how does it come about? If you have let's say this model, then I can construct a following loop operator, that is like I take any loop and I take these radially outwards, these spins pointing radially outwards. And so for example, here at the site number 6, I would take a sigma z, and at this site also I would take a sigma z for the third spin. So this is what I have written. I take a product in this order, order doesn't matter, and I define this star-like object called the loop operator, and I can show that it's a conserved quantity. Flux operators or loop operators of different hexagons, they all commute with each other, and the square of each of them is 1. So eigenvalues are plus minus 1.
You can common side, one common?
Yes. So So therefore, like now see, how many states did you have as such in this n spin system? You had 2 to the power of n number of degrees of freedom in the system, and already you have n by 2 number of conserved quantities, because for n spins there are n over 2 hexagons, and you have n over 2 to the power of n over 2 degrees of freedom already accounted for, because each w can be plus 1 or minus 1. So you still have 2 to the power of n over 2 degrees of freedom to account for and put labels on the eigenstates. So for that, so what Kitaev showed is that the total Hilbert space is divided into sectors. So these are all eigenspaces of these flux operators Wi, and each of these spaces has a dimensionality 2 to the power of n by 2. And within each sector, where flux is kind of some configuration of fluxes is specified, the degrees of freedom are Majorana fermions. And the Majorana fermions come about in the following way. You write each spin operator, say sigma x, as I times a Majorana fermion bx times a Majorana fermion c, and similarly for these. And if you now do the commutation between these, they will obey the usual spin commutation relations, provide you impose this constraint at every site. This is a gauge condition, and with that you have a very good representation for the spins in terms of the Majorana fermions. So what do you get? It turns out that the Hamiltonian written in terms of these fermions is a 4 fermion term. I have hidden some detail here. In fact, this Aij involves a product of 2 B's. So it's a 4 fermion term. So you would think, why did I do this? Because it's still an interacting fermion problem. Well, it turns out that these link fields Uij, which is the product, this is the operator yet, it's a product of these 2 B Majorana fermions. It's itself a conserved quantity. It commutes with the Hamiltonian, and they all these link fields commute with each other. Furthermore, the Uij square is 1, so it's a Z2 gauge field. So it's very much like electromagnetism, except that the vector potential or electromagnetic potential takes 2 values only.
J subscript alpha I j. So what is the J2?
This J is just the overall energy scale. So this J alpha Ij is the strength of the Kitaev interaction, you see.
It's a subscript.
Yeah. So you see these. So you see there is alpha Ij, meaning these interactions can in general be direction dependent. So I mean, you can make them all same, and then everything, all these labels go away.
I just want to avoid such a kiloton kind of.
Yeah. I'm also ending now. So okay. So Z2. So now it can be shown that in this language of fermions and gauge fields, if you write the flux operator Wp, it's simply the product of these Uijs around the loop, which is nothing but what you have, like the Wilson loop-like thing. So about any loop you can calculate this. In fact, this just takes values plus minus 1, because Uijs also take values only plus minus 1. So it turns out that that these gauge transformations, like you can take different combinations of Uijs, they leave the fluxes unchanged. So this gauge constraint Di, which I wrote, it leaves the flux in every hexagon unchanged. So the Hamiltonian is non-interacting in each flux sector, because I can simply replace these Uijs operators by their expectation values. They never change, they don't have any dynamics, and so the Hamiltonian becomes non-interacting in each flux sector, and I have n Majorana fermions. They have effectively 2 to the power of n degrees of freedom in each sector, because you need 2 Majorana fermions to make a canonical fermion, which is spinless, so it has only 2 degrees of freedom. So then it can be shown that the ground state manifolds corresponds to 0 flux in all plaquettes, meaning this is 0. So that would mean Wi equals to 1, and a pi flux would cost a lot of energy of the order of J. So now what is, why am I saying this? Well, you can ask about the lifetime of quasi-particles in such cases also. So suppose I add a perturbation to the Kitai model which
The ground state was non-degenerate in previous ground state.
yeah. So, so suppose I have this JH sigma I dot sigma j, a Heisenberg-like term I add to this Kitai model. Then as I increase JH, the ground state changes from a paramagnetic Z2 spin liquid, which I showed earlier, to some antiferromagnetic order called stripy. And if I keep on further increasing JH, it will ultimately go to some another kind of antiferromagnetic order called the Néel state. And in these magnetically ordered states, the elementary excitations are basically the magnons, which are spin 1 bosons. They are not Majorana fermions, they are not fluxes. So my question is then, if I start with some quasi-particle in the Kitai model, it could be a pair of Majorana fermions or a vortex, and I ask, as I progressively turn on JH, what happens to the lifetime of these? Does it stay stable or does it kind of fall apart? So it's again a question of Anderson localization or delocalization transition in the Fock space. So we have done a lot of exact diagonalization calculations for up to 20 spins. We can go up to 24, but I am showing you for something less, 16 spins. So what is shown here is the following. So I prepare the system in some very high excited quasi-particle state. So in this case, it is a 2 vortex state. Because of periodic boundary conditions, I cannot create single vortex states here. So I create a 2 vortex state, and I ask how this state decays. So in the pure Kitai model, the state is localized in Fock space. Its support is one side. But as I turn on JH, the support extends. And you can ask, so even here, like even though I have made a little bit of JH, I've turned it on, it's 0.2, the quasi-particle is still fairly well localized here, and it decays, it overlaps with a lot of excited states, but these are very small compared to the big ones here. So the support size in this case is not very large. If I, on the other hand, increase my perturbation to 0.6 of the original coupling, then basically my spectrum changes qualitatively. My support is like throughout. So it's as if I definitely have decayed here. Now what we have done is, this is like further increase of coupling shows that the quasi-particle tends to shift to the higher energy end and tries to get localized on that end. So there is a pile up at higher energies.
How do you calculate this? You start with a state and then you
Overlap. No. I calculate exact many-body eigenstates for the n-spin system and calculate the overlaps of this initial state, which was the Kitaev 2 vortex state, with these states.
But
and
which state are you overlapping?
Exact many-body states of the JH plus JK model.
There are many exact many.
All of them.
All of them.
Yeah.
You're looking at the overlap.
Yeah. So now this is an example of. This is just labels the eigenvalue number, and it's increasing order of energy, but different eigenvalues don't necessarily correspond to the same point. The same eigenvalues don't correspond to the same point here because it's just a label, but you can do that also. But it's delocalized in Fock space.
If I understand, you're taking the 2 vortex state in a Kitaev model and just decomposing it into the eigenstates
Yeah.
of the many-body
Yeah,
state.
exactly.
You're saying that in the eigenstates of the many-body state, it has support over many of them.
Yeah, if it has a support over a small number of states, it still continues to be a good excitation even in the presence of these perturbations, which is the case here. Incidentally, this.
So what is the case there?
Oh, that one I don't understand. Yeah, in the other end, yeah, that I don't know. So that I need to think. But you can see that this JH by JK is already in the regime where you have a stripy order. It's no longer a spin liquid, but nevertheless the vortices are fairly well defined entities. It's gone here.
So there's a phase transition at some point?
I don't know, I'm checking it out because we have to do finite and scaling. So I'll show you briefly what is happening. So now if I calculate log of the support size of this 2 vortex excitation as a function of my interaction or perturbation, then initially the support size increases, then it reaches a peak around 1 and then it decreases. But this doesn't mean that you are getting localized again, because I need to know the finite end scaling for each of these points. Because a localized state is one where if I scale with n, the support size will not change, whereas a delocalized state is one where the support size goes on increasing. In particularly for the ergodic state, it should grow like 2 to the power of n.
So you take log x to
Straight line. In fact, that's what is happening throughout the regimes. So this is for the case where the spectral weight is everywhere. This is the truly delocalized state, and you are actually this slope is 1. In fact, the scaling of the support is exactly 2 to the power of n. But if you go to small perturbations, this is still work in progress. But you should not force fit a straight line here under any circumstances. But you see, it's not like whatever you whichever way you look at it, it's not increasing exponentially with n. It might be increasing like 2 to the power of cn, where c is less than 1. This is also a delocalized state, but it's not ergodic. It could also not be increasing, which would mean it is localized. But these we need to check. This is still a preliminary result. And
get this answer from going, I mean, you can go from, let's say, 12 to 20. And this is the old question in numerical MBL also. You know, people know how to go from 12 to 20. But then checking scalings numerically is kind of...
I don't know. I can go up to maximum 24, and that's the end of the story. But you see, IPR also we are doing.
You won't do
but
more
this
than
is
standard MBL people.
yeah.
They do it all the time.
This
Yeah.
problem doesn't not straightforward, because it doesn't become the Anderson that problem.
No, there's no disorder. There's no disorder. So you might get Anderson transition.
You just had this type of
There is only a Cayley tree structure, but it's all regular.
Mappable to a Cayley tree,
That's what I-
that's also not clear.
See, all these Hamiltonians with which connect states locally in Fock space are basically Cayley tree structure. But
Wait, how I can take two things and then come back to the same state? I can
See,
apply the Hamiltonian 3 times.
see, loops are always there. But what is happening is, like in most cases, you can argue that the comeback, the number of loops is very rare, and the contribution they make as corrections to the Cayley tree kind of thing is
You're saying this is true for any Hamiltonian?
not any Hamiltonian of the kind of Hamiltonians which I sort of drew, like the ones which resembled the one I wrote before.
And, what is the class of Hamiltonians that this will be good? Is there some intuition? Because I can take the Fermi liquid clearly as an Hamiltonian. And again, where would this argument break down if I just take the standard clean Fermi C with repulsive interaction? Is it in the mapping to the Cayley tree, or is
You
it
know that breaks down because in Fermi liquid theory you have
you
scaling.
know that the requirement?
Yeah, no, I don't know. So I need to think. This is all preliminary. So in fact, we don't have analytic results yet to compare with a Cayley tree. Besides, this is not a disordered system, so this is not going to have a transition of that kind. Nevertheless, this is actually a very good way to ask about the lifetime of a quasiparticle. Now, there is all sorts of interest in whether you can be in a magnetically ordered ground state, but yet its high energy excitations could be very good topological objects. These fluxes are topologically non-trivial. So you would like to see if these fluxes are still relatively long-lived. So you don't need to know whether there was genuine Anderson localization or not, in which case it would live infinitely long. But you need long enough. Yeah.
But can you do the calculation at infinitesimal JH by?
Yeah, of course. Yeah.
And there can you?
There the support becomes like order 1. It shrinks to 1 or 2 sites.
So you can do that reliably.
Work in progress.
So if you can do it reliably, then you've shown there's a phase transition.
See, what should be really done is, you should be scaling with n.
No, analytically.
Analytically, no, nothing is done, because you see the model is not integrable.
Yeah.
The model is not integrable.
But for it was integrable when JH was 0.
Yeah,
So it's a small perturbation around an integrable.
one could try to do that, yeah.
So perturbation theory should work.
Yeah, it should be some small perturbation around. Incidentally, the
But the question you are asking is about the many-body state. I mean, perturbation should be good, but we usually don't do perturbation theory for getting a many-body waveform. We usually do it for a correlator, 1 point, 2 point, and things and then. I don't know.
but yeah, his point is why not, kind of, some way.
No, I'm saying when he says reliability analytically, it's not clear to me that.
Also, there are various things one could tell, like if you calculate these fluxes, or in particular these uij's, so you can show that the fluxes, while they are well defined for small jh, for 0 jh, they are conserved quantities. The moment you turn on jh, the fluxes are no longer conserved quantities. Now, two things could happen: either the flux can decay, or the flux could be just hopping around, in which case you just get some average value which is neither 1 nor -1.
Suppose I
So-
assume there's a conformal there's a phase transition, then you'll have this conformal field theory at some point. And there, at conformal dynamics, it's always true that you have this spread.
So there is a phase transition between the Z2 spin liquid phase and the magnetically ordered state at JH by JK around 0.15.
You know that there is a phase transition.
There is a phase transition, but these are very highly excited states. So they don't care about what was the symmetry of the ground state. In fact, you should ask what are the natural excitations in the system. Are they bosons, which are the natural excitations of a magnet, or are they Majorana fermions and Z2 fluxes, which is very weird.
Wait,
To
is it a second order phase transition as well?
don't know.
If there is a second order phase transition, because at least there are some excitations, those that are controlled by low energy dynamics, which will always have spread.
Okay, I see.
Because there's a theorem.
I see.
Single particle excitation.
I see. So, all right, this can be checked though, because ground state calculations are much more reliable. So, yeah. So, one can check that out. Yeah. If
Single particle, I don't know whether it was working.
Chalo, yeah. Okay, so I have
Maybe
to.
one theory and maybe
The speaker is going to run away. So because.